Okay, so let's prove this theorem. This theorem says that if f is continuous on a closed interval, then it's actually uniformly continuous on that closed interval. And so just to start off, our goal is going to be to prove that f is uniformly continuous on AB. So what does that mean in terms of the definition? Well, our goal is going to be to show that for every epsilon greater than 0, there exists a delta such that whenever x and y are points in AB, if they are within delta units of each other, then their images are within epsilon units of each other. So the absolute value of x minus y less than delta implies the absolute value of f of x minus f of y is less than epsilon. Right, so for every epsilon, there's a delta, and this delta works for all points x and y in the domain. So let's go ahead and start our proof. We're going to do a proof by contradiction. Here I have the setup. F is continuous on this closed interval AB. The claim is F is uniformly continuous. Now, we're going to do a proof by contradiction. So that means we're going to assume that this is not true. Okay? So I'm going to say here, towards contradiction, suppose it is not the case that for every epsilon greater than 0, there exists a delta such that blah, 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 right? This means, let's put in here, this means I want the negation. So there exists an epsilon such that for every delta, this doesn't happen. So there exists epsilon greater than 0 such that for every delta greater than 0, now what is the negation of for every x and y in here? This implies that. Well, there exists x and y. I'm going to say the x and y depend on delta. So x is going to be a function of delta. And there exists y. Y is going to be a function of delta. So x of delta belongs to AB. Y of delta belongs to AB. These points are close to each other, but their images aren't. So that happens, but the distance between f of x delta and f of y of delta is bigger than or equal to epsilon. So what I've done here is just figure out the negation of the definition of f being uniformly continuous on AB. So I'm saying there's an epsilon such that it doesn't matter how small delta is, for any delta that's positive, no matter how small, I can find an x and I can find a y that are within delta of each other, but they are mapped to points that are far apart, okay? So what I'm going to do is I'm going to let delta equal 1 over n. This will now give me a sequence of points. So I'll have xn and yn existing for each delta equal 1 over n, okay? So in particular, for delta equal 1 over n, there exists xn and yn in our closed interval such that the distance between xn and yn is less than 1 over n, but the distance between their images bigger than or equal to epsilon, okay? So now I have a sequence of xn's in my domain. And I know that because domain is a closed interval, every sequence has to have a convergent subsequence. So xn, right, the xn's form a sequence, and the same is true for the y sub n's. So I'm going to invoke Bolzano-Weierstrass to say that there exists x naught and y naught in my closed interval, and there exists xnk and ynk subsequences such that xnk converges to x naught and ynk converges to y naught as n sub k goes to plus infinity. Okay? So here's the deal. Let me just draw a picture, kind of, to a sketch. I'll draw a sketch so that you can see the problem. Because my function is continuous. I have the x and k's going to x naught. Y and k's are going to y naught. Remember, the x and k's and y and k's are getting close to each other. So I have the x and k's, maybe, here's my x and k going to x naught, xn1, xn2, right? And then I have my y and k's going to y naught, the xn and yn's are getting closer to each other because the distance between the xnk's and ynk's is going to be less than 1 over nk. So if the xnk's are getting close to x naught and the ynk's are getting close to y naught and the xnk's are getting close to the ynk's, that means that x naught has to be equal to y naught. Okay? So here's what we'll say. We'll say, notice that for each nk, the distance between x naught and y naught is going to be less than the distance between x naught and xnk, plus the distance between xnk and ynk, plus the distance between ynk and y naught. This is less than 1 over n sub k. This is going to 0, and this is going to 0. So it must be that x naught is equal to y naught, because I can get this distance less than or equal to something that's arbitrarily small. Okay? Here's the problem. F is continuous. So xnk converging to x naught implies f of xnk converges to f of x naught. And ynk converging to y naught implies f of ynk converges to f of y naught. Right? So f of xn naught, xn k converges to f of x naught, f of y and k converges to f of y naught, right? And f of y naught is really the same thing as f of x naught. But remember, the f of x in k's and f of y in k's are all bigger than or equal to 0. So we get a contradiction because these terms are getting close to this point. These terms are getting close to that point, but the terms are supposed to be staying at least epsilon away from each other. That's the problem, right? So So epsilon is less than or equal to the fnk, the distance between f of nk and fyk, which is going to be less than or equal to fnk minus f of x naught plus f of x naught minus f of ynk. This is equal to f of y naught. This is going to 0 as nk goes to infinity. This going to 0 as nk goes to infinity. So we get a contradiction because this right-hand side is going to 0, but it's staying bigger than or equal to epsilon, right? The epsilon is supposedly bigger than 0. So you can't have this side going to 0, but this side bigger than 0, and this always bigger than or equal to this. So this would be a contradiction to epsilon being bigger than 0, or it would be a contradiction to f being continuous, right? So ultimately, if we suppose the negation of f being uniformly continuous, we get a contradiction. So that means f must be uniformly continuous. And that's it.